This is MEI Statistics Minor Sampling 1.1 Introduction to Sampling. So our first question is, what is a sample? Quite simply, a sample is a subset of the population. Or we may also consider a sample to be n observations from a random variable. Is sampling necessary? Well, the only alternative to sampling is a census, where the entire population is considered for survey or experiment. Now this is problematic for multiple reasons. A census may be difficult, expensive and time consuming. So think how big a deal the UK census is every 10 years. It is a multi-million-pound enterprise. Sometimes the extent of the population is unknown. So imagine if we were looking at wild lemurs in Madagascar. We certainly don't know how many wild lemurs there are. The entire population may not be reachable for survey. So for instance, if our population were of drug addicts, we wouldn't necessarily be able to contact all of those people. Sometimes sampling is destructive, and so a census would be inappropriate. For example, testing the lifespan of a light bulb destroys the light bulb. So if we destroyed all the light bulbs, there wouldn't be any light bulbs left to sell. The size of a sample can greatly affect the interpretation of an effect size. For my first example, I've got a quote. I tossed a coin repeatedly and it showed heads every time. It must be a biased coin. Well, that entirely depends on how many times you've tossed that coin. In case A, if you've got n equal to 3, well, the probability of getting 3 heads by chance is a half cubed, which is 1/8, or 0.125. Not that unlikely at all, really. If you have n equals 20, well, the chance of 20 heads is quite something different. That's 1/2 to the power of 20, which is 1/1,048,576, or 0.000000954. I'd say we've got a stronger case in case B for the fact that it is a biased coin. Example 2, another quote. 80% of those sampled preferred our brand X to our competitor's brand Y. Well, again, it depends on how big your sample is as to how impressive that is. If n is equal to 5, and I did a quick test, use the 1% level of significance, define our random variable as the number of people in the sample preferring brand X. So, if n is equal to 5, X is distributed binomially with 5 trials and P probability of success. Our null hypothesis would be that the population has no preference. So P is equal to 0.5. Our H1, assuming we're doing a one-tailed test, is that the population prefer brand X, and so P is greater than 0.5. Now, if 80% of those sampled prefer brand X, that means 4 of them. So we want the probability of 4 or more. Probability that X is greater than or equal to 4 on your calculator is 0.1875. Not a very strong case, certainly nowhere near that 1% level of significance. I'd say it's significantly greater than 0.01. On the other hand, if we have n equal to 30, and we have 80% of those sampled, that's 24. If I run through this, the probability that x is greater than or equal to 24 is 0.000715, which is significantly less than that 1% level. If we have n equals 100, 80% is going to be 80 people, and the probability that x is greater than or equal to 80 in this case is actually 5.58 times 10 to the minus 10. I'm quite convinced now. Example 3, my data shows perfect positive correlation between x and y. Well, if your number of points is equal to 2, that's not all that convincing, because any 2 points I can stick a line directly between them. Or over here, it is always perfect positive correlation when n equals 2. If n equals 3, well, we have something there. It may be convincing, but it might also just be a coincidence. Whereas n equals 10, if we get data points like that, we are absolutely positive that there is some perfect correlation between the two. In our next video, we're going to be doing sample features.